Okay, do I need to stand up?
You can do whatever you want.
Okay, I can do it from here.
Welcome, everybody.
Welcome, everyone. My name is Enrico, and I work at Macchina IO team inside the PSC. So yeah, if you want to come closer, we can make it more interactive. So the goal of this presentation is to really introduce IO from a new approach. So because I also am relatively new to IO. I learned it from the first time at DevCon last year. And let's say I've been trying to understand it until now. And I kind of now found an approach that made sense to me. So I wanted to share with you. So this was basically, I think, the starting point. That was kind of difficult for me to make sense of. So because on one side, I found this a lot of, where is it? Well, it's fine. So on one side you have these IO papers that are like very, very deep, and they require knowledge for like, I don't know, there's a long line of work that you need to know about in order to read the paper. And on the other side, actually, it's not like that big of a site, but there are like some resources about IO that are like, let's say, for newbies. But what they really tell you about is what IO can do. So maybe you can understand at the high level what are like the capabilities, the affordance of IO, but it doesn't really tell you how to build it, like what's behind it. And it looks just, okay, there are like some APIs, but what's really under the hood? So what I'm trying to do in this presentation is to bridge this gap. So it would be very arrogant to claim that I can bridge this gap in an hour or so. But like my goal is to give you this new perspective, such that like the problem IO, we kind of reduce this to a smaller problem, and hopefully by the end of the presentation, I can give you this map that allows you to approach the problem. So if you want to study more, you have I don't know, like a map in mind, and you can map it out. What are like the building blocks, and you can, I don't know, at least in your mind, I think it will be a simpler approach. And also, I think we can make it interactive. Like, so if you have any question, we can also use the whiteboard or whatever. Just ask me if you don't understand anything. I think I can take as a goal that you all should understand everything by the end of the presentation. So if you don't understand something, just let me know. So we are gonna take this presentation as a more like a iterative approach. So we are gonna have a goal, like a engineering goal, and we are gonna try to use like different cryptography that we kind of know, or that we are gonna know throughout the presentation, and try to build this application. So the application that we want to build is, I will claim, simple, dummy. So it's I call it like a non-interactive conditional signature printer. So this is like the API of this program. So it's simply a functionality that takes as an input like a key, K, and some input X. And this function is going to check if the X is a prime number, and if so, they're going to sign this prime number with like this signing key K, and just return none otherwise. So what does it mean, like the name, like what are like the requirements of this application? So we know what conditional means. So the condition is expressed by this if-else statement. The non-interactivity property is very important. So we want someone to be able to consume this program in a non-interactive way, meaning that, so let's say that we have like two sets of users of this application. So there's like on one side a key owner. So this guy is the one that owns this signing key, and this is also the one that deploys the program. And on the other side, we have a set of users. We might have like Alice, we might have Bob, we might have Carl. And these guys are going to consume this program. So they are going to bring the input X to this program. And the non-interactivity factor requires that they should be able to run this program without speaking to the key owner. And we don't assume any, like, let's say, knowledge about the user from the key owner. So they might just pop up in the future, and the key owner shouldn't know who's going to interact with this application. And also a very important requirement is the security. So the security means that the key, K, should not be learned by this user, Alice, Bob, and Carl, because otherwise it would just make no sense at all. So of course, like, you can think of a very dummy solution, just like publishing the source code. And of course, this will be non-interactive because Alice, Bob, and Carl can run it. But this will break the security of the application because anyone will be able to basically read the key.
Do you think about Alice, Bob, and Carl in this model, like unbounded computers, or like what they are?
So they are just, so I'm not going to give like a precise security definition, but they are just simple users. So they're not. Want to join?
No, I'm looking for Shaka.
5 minutes ago.
So no, we don't assume any exponential capability from the users. So they just, I don't know, let's say they have, they just enter the input and they just want to get something back. Okay, so this is like our setup, and our goal is to build this. So maybe, do you guys have any suggestion? Maybe you know what's the solution, but let's try to think just some random idea.
They put MPC in the center.
Yeah, there's a solution that is based on that. But so what would be the MPC? Because remind that we don't want, so this guy, like, they should just do the setup phase, do something, and then disappear forever. So like the interaction with this program is delayed from the user side. So if there's some MPC between Alice and the key owner, is breaking this interactivity requirement, non-interactivity requirement.
No, the key owner will set up the MPC, but without his own participants or his own participation. He won't need to supply an input into MPC, and MPC will just be available for the rest of the users, where you can do that. Like, for example, you can have some, I don't know, obfuscation of inputs where one user puts one input and some inputs magically appear there.
Yeah.
So they do not know.
Yeah. Actually, it's let's say abstract, on an abstract level, is very similar to the solution that we're gonna land to eventually. But we're gonna do some more steps. You wanted to say something?
I mean, you want to scale the program.
Yeah, that's true. So we can go home. So I'm gonna just go. Yeah.
And if, for example, I know it's not possible because it's the introduction of the talk, but like, let's say that we want to use FHE, for example.
Yeah.
We want to encrypt like our TK.
Yeah.
And like encrypt it with FHE and post it somewhere. Like, would all other participants would be able like to use this encrypted key?
Yeah. We're gonna go through that. Yeah. So we're gonna go through a set of attempts until we find a solution. So we're gonna start with another naive solution. So we just call it like a public lookup table. And actually, a public lookup table is itself a sort of like a solution to obfuscation. So a public lookup table just means that this key owner is going to publish a lookup table that maps for each input xi in this input domain the solution yi. So they're just going to basically take any number from 0 to a bound that the key owner is going to choose, and they're going to sign this message if the sign this number if the number is prime, or just return 0 if this is not prime. And so I'm not now discussing about the security of this solution, if this is potentially gonna break the security of the key, but just from a simple like a effort perspective, you can see that this solution is not really sustainable because it's kind of exponential to the input bit size. So if we just set even just, I don't know, 64 input bit as the input domain of the input x, it's going to require like 2 to the 64 efforts, computation efforts from the setup owner. So this is not going to be sustainable for like real world application, and therefore we add an extra requirement from additionally to the two that we introduced before, that we don't want the key owner to have an effort that is exponential to the input bit size. And we're going to see later why we want to set this requirement as well. Okay, so this is not the way to go. The second attempt is going to be, as Yannis suggested, FHE. And we're going to also present what are like the APIs of FHE, just to give you some refresher on that. So note that this is like a secret key FHE. Just for simplicity, I'm going to use secret key FHE. So there's like a key generation phase that returns a secret key, an encryption phase that encrypts some input k into CT of k. There's the evaluation phase that evaluates a function f on the ciphertext. And eventually we can use the decryption key, the secret key, to decrypt a ciphertext. So the only difference between secret key FHE and public key is that you also use the secret key for encryption and you don't use a public key for encryption. So given that, we're going to try to build this non-interactive conditional printer with this FHE. And this is like the graph on how I was thinking about building this application. So like in the middle, you see there's this cloud. So the cloud really means just like a publishing to the public, because we assume that there's no interaction between the key owner and Alice. So in theory, the flow from the key owner should stop here. They need to do some setup, publish, and then they wouldn't appear anymore, because otherwise it will break the requirements. And you already see that this is broken in a way. So they will.
Can you tell once again what is the difference between key and secret key?
Yeah. So secret key is the secret key for the FHE scheme.
Oh, okay.
So k in this case is an input. I just put it k because in our application the signing key is k, okay. But it can be whatever really, any input. So the key owner encrypts this signing key k, publish the ciphertext, and now any user, Alice, Bob, and Carl, can take this ciphertext and evaluate this function f. So the function f is public, and they can evaluate using as an input this ciphertext for the signing key. And in this case, I just set Alice input as 7, and now they obtain a ciphertext that actually contains the output of this program that generated by the key owner. But still, there's a problem, as you can tell, that FHE somehow requires decryption. So the problem is that Alice by herself cannot obtain the output, which is this f of k7 by herself, without interacting. The only way is just sending it back to the key owner, ask them to decrypt, and eventually the key owner will send the decrypted output to Alice. So we can see that there's an issue, that it requires interactivity during decryption. And I think you cannot really escape this. I think this is this is basically how FHE is designed. So it gives you freedom. So on this evaluation step, you have a lot of freedom. You can really evaluate whatever you want, any function that you want. But the drawback of this freedom is that in order to decrypt, you need to come back to someone that will authorize this decryption. And of course, if the key owner would publish the secret key, this will again break the security and not gonna work. Clear? Okay.
You can't take it because we need non-interactive.
Yeah, no good solution. We're gonna discard it. So now I'm gonna introduce a new technology, which is functional encryption, which I'm aware that is not very hyped or famous in our space, and I think the reason is that it's really difficult to find utility for this, but we're gonna see why it's useful. We're gonna see an application that is like a real-world application of functional encryption, and then we're gonna see how this is also gonna help us to build I/O. So these are like the APIs for functional encryption, and we are gonna go through that. And so now I'm just going to read the API, but I think later when I show you an application, it will make more sense who's doing what, because this is most difficult part. So there's a setup phase that returns a master public key and a master secret key. Then there's a key generation phase, which is tied to a function f. And this key generation phase is going to return like a functional secret key. And then there's an encryption step that takes some message, in this case k, the master public key, and returns a ciphertext. And the cool part is this decryption step, so that you take a ciphertext and you take a functional secret key and you can obtain f of k. So you can maybe, if you want to find an analogy with, let's say, a parallelism with FHE, is that in FHE we had the evaluation step and the decryption step that were like the evaluation, and we had like this freedom in the evaluation, but then the decryption was, you need to come back to the key owner, to the decryption. Well, here somehow you blend together the evaluation and the decryption in a single step, but you don't have the same freedom, because the only thing that you can get is the evaluation of f of k, and this f was chosen in this key generation step. So I think now I'm going to give an example that will make more sense.
Is it similar like to witness encryption in the sense that our key will now bind it by a challenge?
So I think a difference with witness encryption is that in witness encryption, you encrypt some value, x, you get a ciphertext of x, and then, so the encryption is also tied to some like problem or like challenge, and whoever is able to solve this challenge is able to decrypt to obtain the x. So the difference here is that you don't get the encrypted value itself, but you get a function of the encrypted value. Okay. So it's kind of different. So you don't get like a...
Just a random question. Why do you say it's not popular in this space?
Because no one found maybe a utility in the blockchain context, I guess. Maybe I'm wrong. It was just my sentiment.
No, I've heard it twice this day.
Oh, okay. So it's positive. Maybe it's getting more popular now.
No, I've heard twice that it's not popular yet. So
So what was the context in which they were also speaking about functional encryption?
It was the FEMPHD for Bitcoin pipes thing. Yeah, and it was Lisa that said it was not popular.
What?
The witness encryption thing.
It's not witness encryption, functional encryption.
Yeah, so witness encryption is...
Witness encryption, we do not know how to do witness encryption.
So,
Yeah.
so actually...
But also somebody else also said this was not popular, so it's just...
Yeah. But so just a side note, if you can build I/O, you also get witness encryption as a side gift. But I think, we forget about witness encryption now. So we're gonna just see an example why function encryption is useful, and this is just a non-blockchain or Ethereum-related example. So the context is that we want to build a secure email spam filter. So the setup is that there's like a user, again Alice, and can see. But on the other side, she also doesn't want like an encrypted email server that cannot filter emails. So if all the emails are encrypted, like of course like some server cannot tell which is spam or not. So she need to get everything, decrypt, and tell manually what are like non-spam or spam. So this is the motivating example. Okay. So this is like the solution basically to this dilemma that Alice is facing. So she's gonna run this initial setup, obtain this master public key and master secret key, and then she's gonna provide her email client to a functional secret key. So this API, and she's gonna set this F as a function that is able to detect whether an email is spam or not. So let's say just return 1 if an email is spam and 0 if not. And what is going to happen then is that any email sender that wants to send an email to Alice will use her master public key, and this K in this case would just be the email itself, and encrypt the email, and the email client will like receive encrypted form, and what the client is going to do is they can, given the ciphertext and this functional secret key related to the function f, they can now run the decryption and obtain f of k, which will be f, like this spamming detection function, on the email, and just obtain 1 or 0. And doing that, they can serve to Alice only the emails that has passed the spamming filter and just throw the other ones away. Makes sense? The setup. So this is like, so we have basically like two, I won't say anything else if it's clear. So this is like a motivating example of function encryption. And remember that our goal was like to use, maybe try to use this technology to build our non-interactive signature printer. So maybe, do you have any idea of how this can help, or at least some intuition of why this might be useful for like our goal?
Because you have this sandwich construction of like encryptions that they won't need to get the output, the result. They won't need to call the key issue again.
Yeah. That's exactly the point. So the cool part is that on one side we have this key generation that binds the function to a specific one, to f, and the other cool property is that the decryption is non-interactive. So we kind of lose the freedom by binding the function, but then we gain on the non-interactivity of the decryption. So this is what we're going to use to try to build.
A bit on functional encryption overall, like how practical it is, like what are the main schemes used, where.
Yeah. I'm gonna go through that because the spoiler is that you're gonna go through function encryption in order to build I/O, and this is also not practical. So that's the sad news.
It looks a bit too good today.
Yeah. But so at least I guess my opinion is that like just approaching the problem as building function encryption seems less scary at least than just saying I/O. It's like okay. So this is how the sequence diagram for the effort based on FE to build our construction. So we really have only like 2 people in this scenario, or let's say many users, but we just focus on a single user. And you see that we already breached, so there's no interaction with the key owner after this point, so this is good. And in this scenario, the key owner is going to encrypt the signing key K, and they also going to generate a functional secret key for the function. And I also skip the setup, but of course the key owner is doing the setup. They're going to generate a function secret key tied to the function f, which is the function that we defined originally. They're going to publish these two. So the ciphertext and the function secret key are published to anyone in the world. They can be consumed by Alice, and so ideally we should do this. The decryption starting from the functional secret key and the ciphertext to get f of k and 7. But maybe you can spot why there might be some issue here.
How did they add the 7 as an power?
Yeah, exactly. Because like, so the way that the function must be designed, so let's say this function, the way it is designed is that it takes only a single input. So the key owner can design it such that it takes the k as the input, but we cannot really add the dynamically chosen input by Alice. So there's a way, as you noticed, it doesn't allow Alice to inject a new input to this decryption function. And we could think about like a dummy solution to that. And in this dummy solution, basically, the functional secret key will be generated for a function that hard-codes the possible inputs of Alice. So we define the function in this way, but we run into the same problem that we run with the public lookup. So this is again exponential to the possible input size, to the input bit size that any user is allowed to choose. So I mean, there's still something cool here, but this is not enough. Function encryption is not enough because of this requirement.
Can you explain it again?
Yeah. So, like the way function encryption is designed is that the key generation is for a function that takes a single input. And in this case, the single input is the input that is being encrypted by the key owner, which is the signing key K. But actually, what we want to do is not allow Alice to run f of k, but f of k plus some input that is dynamically chosen by the users and that the key owner cannot know about in advance. So what we do to find a solution for that is like to allow the key owner to generate the secret key, the function secret key, for as many functions as there are the possible inputs of the user. So in this case, basically the input is just hard-coded inside the function. So really we are still in the setup in which there is a single input. And the potential input of the user is hard-coded into that.
But how is that then different from what you mentioned in the very beginning?
Yeah.
Just do a lookup table for everything.
Exactly. It's not different. So
Okay.
this is not the solution. But we're getting there. So now I'm just gonna present I/O in a different way, and basically we just think about like this imaginary API that if it existed, it would actually give us a solution, and we call this API extend ciphertext. So basically, really, this API just takes a ciphertext and an input X and kind of concatenates this input inside the ciphertext. So it's just adding something to the ciphertext. And we can easily see that this provides us a solution for this problem. So basically, the role of the key owner is still the same. Everything is still the same, basically. We just added this API such that Alice can take their input, add it to the ciphertext, and now she can obtain the result f of k of 7, starting from the ciphertext that was provided by the key owner that only encoded this signing key. So, I mean, I'm not really giving you anything crazy here. It's just a different way of seeing an extended version of FE, an augmented version of FE that actually gives us I/O. I mean, we didn't even define I/O, but this is basically I/O. So we can see that there are all the original requirements were met by this solution. So we have the non-interactivity because the key owner can just disappear at this point and it's still possible to carry out the computation. It's secure because this is, I mean, I didn't explain you why this is secure, but the definition of functional encryption, the security definition, guarantees that the ciphertext itself, let's say informally, doesn't reveal anything about the value k, which in our case is what we want to protect. And the only thing that gets learned by Alice is this f of k of x. So as long as this function doesn't reveal information about the key k, this is secure. So Alice doesn't learn anything about the signing key k. And lastly, we also meet the non-exponential effort because we can see that the functional secret key is not dependent on the input of Alice as it was in our previous non-successful effort. So, okay. So now we're just gonna do a sort of like a cleanup of the interface, and we're gonna just basically change the way of interpreting it in a way that meets the APIs of I/O. But really, it's not. There's not any difference in the meaning, in the substance. So we're just gonna define the three APIs: the setup API, the keygen API, and the encryption API, as this obfuscation API, and this obfuscation is going to take a function f as an input together with like some secret k, and this means like there's just some input space that is not known yet at this time, and this is going to return an obfuscated circuit, and starting from this obfuscated circuit, the evaluator, which is like Alice, Bob, Carl, whatever, they can just add their input. This should be on the other side, and obtain the function of fkx, which in our case is like either the signature or not.
At what point did the circuit enter the room?
It's just a way of calling it an obfuscated circuit. We can just call it like obfuscated program or obfuscated artifacts. I haven't. So basically like these four artifacts, polynomials, whatever, matrices, they become the obfuscated program.
Okay.
So this means that this obfuscated program can be published wherever, and it won't reveal any information. And just by updating our setup, the key owner runs the obfuscation, publishes the obfuscated program, and the obfuscated program can be consumed during the evaluation phase. So again, I didn't change anything. It's just a cleanup of API and function definitions. So basically, this is just a recap of what we built. We are going to use this graph later in the presentation. So this is just the definition of the function. But I think you can imagine this square as as the obfuscated program. And everything that is in white is actually public, so we know the function definition, we know what this thing is doing, but there's only one part that is secret, which is this secret signing key K that is used for signing. So actually now we can either go into the application and come back at the end on a bit of theory. Maybe, what do you prefer? Application or just a bit of theory? Okay, so I just want to give you, because I promised you at the beginning that I was gonna tell you like how this is built, but I didn't really tell you much about this. So I just have this slide that I think is the core of the theory. And so basically like this encapsulates the map of building I/O. So really what we is a way at least to reduce the problems into something that might be more familiar, or that is honestly like if you pick each step, it's not that difficult to understand, to learn. So we have like the core building blocks are this BGG encoding and the lattice trapdoors. So BGG encoding is basically a way to, well, I don't know if we should, maybe we can see it later. I don't know. I also have slides for this, but it might be too deep of a rabbit hole.
3 sentences say
So it's really like,
approximately what?
so it's a way, maybe I can, oh, these slides are private.
Yeah, just
No, I'm joking.
at least have an intuition about like what is this extension operation that we are performing.
Yeah, so basically like the point of BGG encoding, so let's not, why? So the point of the BGG encoding is that this is, so you have like this encoding, let's just treat it as, without going too deep into what's inside. But there's like a value X inside that, and there is a matrix A, a public matrix A. And every time that you do computation on top of this, you will update the value after an addition and the public matrix. And the same for multiplication. So you're going to update the public matrix and the value inside of that. And the core property is that this is independent of the value, but it's dependent on the computation that you're doing. So in some way, this component of the BGG encoding keeps a trace of the computation that you've been doing, but is not dependent on the input. So the next step is that you can use this thing called lattice trapdoors to provide a way to the evaluator, in this case, to just remove this step and obtain this thing in a way that is binded to a specific computation, even before knowing what's going to be the input here. Very, very brutal way of explaining it, but this is the key property that allows the obfuscator, the key owner, to establish a specific function and provide a way to the various users, to the various evaluators, to basically obtain an output only on their inputs, only if a specific computation is performed, is run. So there's this binding phase that is done here. And this is not I/O. This is like this is functional encryption. And I wanted to point you to this paper that is AKY24. Maybe we can. So this is the paper that was the most important for us. We spent a lot of time on this paper, and I also probably suggest you to go through this version if you are really interested. This version, not the latest one, because the latest one has some fix because of some attack, and it becomes a bit more messy. But like the core idea is still the same as in the previous implementation in this version. And so really the difference, sorry, this is another presentation. So the point that I wanted to make here is that if you understand like BGP encoding and lattice trapdoors, you can build functional encryption. And the next step, what we really did in our paper, in the Diamond.io paper, but this is not the only paper that has been trying to do that, is add this additional API, this augment FE API, and this leads us to IO. So it's not that crazy, honestly. Just need FE, and this is not our goal, our issue, and we just came up with like something else that allows us to let these evaluators add their own inputs.
But it means you will extend matrices.
Extend matrices? Yeah, I mean it's a bit more. It's a kind of. It's different. It's more like a. We use some trapdoors that they have like some mathematical definition that allows to add more inputs. But I think I shouldn't go through this route now because it's probably requires a lot of knowledge. But probably.
No, I'm just curious from the perspective how bad it is in terms of the size of operation.
So it's not. Well, it's a bit bad. So we have some probably benchmark somewhere. So this is like the results. So we just we have like a circuit that is taking some bits as the input, and then is performing some operation. Maybe I think we are doing like one addition, one multiplication, and then doing the decryption. And these are the results. So you see that so we separate it between like obfuscation time and evaluation time, and you see that the obfuscation times is somehow sublinear, if not exponential, to the input size, and the input size is 1 to 4 bits. So it's not that we are saying that this is practical, but two things that are promising are, well, first of all, is that a huge improvement from the latest state of the art, because now it takes 6 hours, considering like these circuits, compared to this old paper that was saying 10 to the 27 years. And one good thing is that, as we notice in our description, like the role of the key owner, the role of the obfuscator is just a one-time setup thing. So we are kind of trying to build it in a way that we push the trade-off on the obfuscator side. It's similar to like if you want to build like a ZK system that pushes all the hardware on the prover side, and just the verification is very, very succinct. We are kind of doing something similar. So we are assuming that the obfuscator might have some huge hardware, some GPU parallelization, whatever, to run this setup. And then the evaluation phase should be very, 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 very lean, should be very, very fast. So I'm not saying that this is fast, but at least the trade-off is going this way. And I think this is promising. So you want to go to the application, or? So the application, I was just, like my motivation was like explaining how to build encrypted smart contracts in a way that makes sense. Okay.
I think you have so many applications for it if you can build it not only in the kind of.
Yeah, so I think this is like a general application, like encrypted smart contract is a umbrella term for many applications.
But you can then just encrypt computer program, not necessarily smart contract.
Yeah. But there's also like a. Yeah, that's true. But like if you really want to, I think there's a sort of like a trade-off there, because if you want, you can potentially, of course, obfuscate any program, but this will require a sort of like a program-specific obfuscation. So you want to do a program for, I don't know, voting, then you obfuscate this. You want to do a program for like matchmaking, you obfuscate this.
Yeah.
But we're also looking, because we know that obfuscation is expensive, so we are trying to make it such that we can obfuscate the smallest possible program that can help us then be reused across all the other applications. So a sort of like a one-time setup that can then people can create application on and just use the obfuscation for this very specific action, which is still like the fundamental action for any of these applications.
And just there is something that is blurry to me. So in terms of the bits that you have to obfuscate, it's the circuit actually that you're going to perform. And I don't have any intuition about the bit representation of the circuit and what the circuit is performing. Because like the benchmark doesn't seem like that afraid. I'm not afraid by the benchmark, but I don't have any clue about like even a simple program. Like what's the size of it?
Yeah, okay. Yeah, I think my setup wasn't very clear. So what we are doing, so if we define it as like what you're obfuscating, because I've been told that I need only to use this portion of the whiteboard. So, like what you're obfuscating, the obfuscator is obfuscating like this program. So this function f with some k and some dynamically chosen input. And this is like the bits. So when we are saying like 1 bit, 2 bits, 4 bits, we are just worrying about this part. So we're like the program itself, the one that we are running, the function is defined that I think it just multiplies the k with the input bit, or it just add the k with the input bit. So it's really not really a meaningful application.
So in the problem you framed in the first place about like the conditional signature would be our x.
Yeah, exactly. And the f will be designed to do like this check and either sign or not. But this is like the circuit definition that is embedded in the obfuscation. So I think there are like two set of like variables that influence the cost of the obfuscation. So one is the size of the circuit that you want to execute, and the other one is the size of the input bits. But as I mentioned, like really our effort is focused on this extend ciphertext API. So everything else, well, actually we are also working on that, but it should be somehow outsourced to like the functional encryption guys if they were doing their work. So that's why like our benchmark explain you what is the cost of like in terms of like user input bits, evaluator input bits.
Why did you decide to work on that?
Because it's cool and it feels like so we have like this idea that like maybe I can also give you, well, I can just explain it to you. Like we feel that like in the long term, like this private state shared state computation application, if they work as expected, like the value locked inside this application will grow up, will accumulate and accrue. And if we rely on MPC or FHE on that, you will always have this issue of collusion risk. You know, I didn't go through that, but multi-party application based on FHE or MPC are subject to this risk of collusion, and potentially people can just decrypt and access values without being accountable for it. So like our thesis is that really this application will never scale because of this issue. There's always going to be a value that will make people betray the system and just decrypt everything. And while by building this application with I/O, we kind of remove this risk. And I think this, like personally, that was the reason, because I work with MPC and FHE, but I was kind of dissatisfied by this. There was also this thing that I couldn't not think about. Okay, so let me go through this. Maybe we can do it in 15 minutes, 20 minutes, and then have lunch. Okay. So the application that I wanted to take as a real example for I/O, of course, is not the non-interactive conditional signature printer, but we're going to see how really we can easily extend this application to something more meaningful. And this is like a slide that I took from Vitalik recently, and well, it was just basically saying like the possibility of having privacy of rights on chain. So having these applications such as voting, DeFi, whatever, private. So maybe the first question that I ask you is like, I know that Lisa works at Aztec, so why you cannot build like a private DeFi on Aztec?
You can build private DeFi on Aztec.
How?
Write smart contract.
So let's say voting, because I'm going to use this as an application. So when I mean like private voting, I mean an application in which you can like the result. So I have actually, no, don't go, let's not go there. So the votes are private, okay? So I just cast a vote that is like 1 or 0. Everyone cast their vote, and you want to just obtain the final result. Either this, I don't know, this law is passed or not. If there are more ones than 0, it's passed, otherwise not. How can you build this with Aztec?
I don't know, write a smart contract where vote is a private variable, then everyone is voting privately, but after that, the function that counts all the votes, make it in a public way so it's verifiable. You can build it on Aztec. There is a tutorial on Aztec docs of how to build private voting.
So, like the function that is able to compute the result in a verifiable way must have access to the votes in plain.
Yes, but it doesn't know from whom.
Yeah. Okay. That's a good point. Yeah, absolutely. That's doable with Aztec. But still, this reveals the votes itself. Let's not argue about like the usefulness of this.
For DeFi, it's more complicated because you need shared states for composability, and if everything is private, it's maybe harder to do like by discovery, like building Uniswap on Aztec.
Building ZK-MPC is easier than building AO. But you can't do Uniswap private. You can do only identities private, but you can do limit order book private. But through ZK-MPC, and then your your order matching is pretty much checking every order up against every order, so it's not very useful.
So, well, basically like I think you said MPC a few times. So, yeah, like you can build this with MPC, that's true. And I think the point is that, so the order book example, I think then you're fine doing with MPC. I'm totally fine with that. It's like what Renegade is doing, like matching.
Fine, but like so fine.
Why not fine?
Because if you want to do it in a private manner, that like it's only I want to trade, I put my trade, you want to trade, you put your trade, and you want the third party or whatever not to get access neither to my input nor to yours.
Yeah.
The only thing you can do is checking every against every.
I see.
You're kind of brute forcing
Yeah. Okay.
order matching mechanism.
Well, I'm not sure, like, what's the design that you have in mind.
Maybe FHE then?
Yeah, that's actually what I was going for. But so, like, the point that okay, let's go through this and see the point that I'm making. So this is like the private voting application that I was mentioning. So we just really want to keep the vote private. So I think if we want to give a justification for that, is like we don't want to know if it was like 99% one or 51 or 49. We just want to know what is the result. And the requirement is that until block T, everything should be private. After block T, only the final result, either passed or not, should be revealed. And there's an effort to use like FHE-based virtual machines, basically a FHE rollup that is, for example, done by Zama, and they just design smart contracts in an encrypted way. So the encrypted smart contract, in this sense, means that the state inside the smart contract is encrypted under FHE, and any state transition function is an FHE evaluation, and the smart contract itself is going to set the decryption rules. So who can access and when this can be accessed. And we can build our private voting app with that. So each vote, so the state is the partial result of the referendum, of the election. And the state transition is really just taking an encrypted vote from a user and updating this state. And the decryption rule is set such that the decryption is public, so everyone can execute the decryption of the state only when block T is reached. So does this make sense? Yannis?
Yes, so you don't know who voted what, but you know who voted, like in that set.
Yeah, okay. So, I mean, the who voted part, we can protect it with ZK. So, let's just outsource it to some other technology. If we care about this, we can do that with like semaphore or something like this. So the issue with that, I think I had the animation to avoid the spoiler, is that what I was mentioning before. So given FHE, given how we describe even FHE originally, there's always this coming back to someone to do the decryption, and so we need someone to hold this secret key, this decryption key, and of course, like giving it to just one person is not acceptable. So what at least Zama proposed in their paper is to kind of split this key across a committee of people. So they have n committee members, and by pulling together at least T of them, they can decrypt something. So if there's a vote to be decrypted, a state to be decrypted, you just broadcast your request to this committee, and someone will say, okay, yeah, I'm gonna give you my decryption share, and by pulling together this decryption share, you can obtain the decryption result. And the risk, as I mentioned, is that there might be misuse of this decryption key, but I think one important point that not many people really speak about is the fact that this can be something undetectable. Because when you speak with like Zama people, so they say that, okay, but this is like a Ethereum consensus, like we are relying on a committee, and they can either behave in a good way or bad way, but it's still the same security assumption. But it's actually very different, because in a Ethereum consensus, you can detect someone that is, for example, broadcasting a block that is, I don't know, it has some issue. But here, you can think about like these committee members. They can literally just meet in this room. They can pull together their decryption share and potentially decrypt the whole state of the blockchain. And this will go undetected. So there's no, you cannot really account for them in a way that you can maybe then penalize them financially. There are some papers for this topic, which I think is also very interesting and under researched. And the keyword is this traitor. So I think this is the paper, traitor tracing for. So there's like this paper about like accountability for misbehavior in threshold decryption. So this is exactly what I was describing, and but I honestly tried to read this paper, and it doesn't really seem something actionable, like something that you can see, okay, let's go and try to implement it. It's very abstract, and I didn't really understand it, to be honest. But so this is honestly a very interesting topic that I think, if solved, could help a lot. This FHE, let's say FHE-based private computation systems, to add like some sort of accountability and financial slashing mechanism, etc. So anyway, what I was gonna go with is that we can find a solution for that with I/O, and the cool part is that we don't really want to change the setup. Like the Zama FHE VM can stay the same, can keep existing as it is. We only change the component for the decryption part. So rather than relying on this committee, we build a conditional decryptor. We obfuscate this conditional decryptor. We publish it, and then like everything else can remain the same. And every time that someone wants to decrypt something, they can go and basically obtain the decryption. But that's the conditional part, because of course we don't want them to just decrypt whatever they want. And we design it in this way. So like what I'm presenting here is like how to design a program that, if we are able to obfuscate it, is a kind of relatively simple program. If we're able to obfuscate this program, we can extend it to potentially obfuscate any program. So we kind of use the FHE EVM as an infrastructure to just keep state private and manage state transition, etc. And we only rely on this small component, relatively small component, for the conditional decryptor, such that we remove the trust assumption in the committee members that is introduced in existing FHE VMs.
Can you repeat? This program will take as input all the signatures from like a set of validators.
Yeah.
And then say if the quorum is n out of m, then I release the description key publicly.
So we completely remove this part. Like the committee doesn't exist anymore. So this is just cut off and replaced by this. But so you're right. Like the point I think that you were making is that there still must be like some way to like reach consensus on what needs to be decrypted or not. So it's not out of thin air that you can tell if something can be decrypted or not. And this will rely on like a consensus proof. So we can, for example, think that in our voting application, the smart contract that is handling this application is designed in a way that there's a slot. So I'm not super familiar with like a state tree and etc. I think you're more familiar than me. But like so let's assume just there's one slot in the Ethereum state, and everything that goes into this slot is allowed to be decrypted. Okay, so this non-interactive conditional decryptor will take a consensus proof that is signed by the set of Ethereum validators. Again, I'm not an expert of that, but I assume that eventually it's basically a signature proof at the end of the day. And this consensus proof will tell that there's a ciphertext CTY in this slot. And if this proof verified against the set of validators that sign this state, we can then proceed and decrypt. Otherwise, not. So I think if we really want to, boil it down to a simple concept, what we are really replacing is the MPC for the committee chosen by Zama, etc., is replaced by just the Ethereum consensus. And we let's say, I'm not saying that we remove completely like any trust assumption.
But now it's on-chain.
Yeah,
So
exactly.
Yeah, that's the most important part.
Yeah,
it's not about who is deciding, it's about like being able to audit the fact that someone
Yeah.
did something.
Yes.
I thought that once you decrypt with Zama and FHE, you decrypt everything. Now you have to re-encrypt.
Yeah.
You decrypt just one slot and not the whole everything. So maybe I misunderstood. I thought that because they need composability between the components, the entire network, like if Phoenix, is encrypted with the same key.
Yeah, correct.
So how do you decrypt just one thing and not the whole thing by mistake, or
So
is it part of the obfuscation? Or?
So if something is not, so there's like basically like the way the smart contract is designed is that it has some decryption rules, and the way also this proof verification is designed is that, let's say, it is already assumed to know this decryption rules. So if something, let's again take the example is that everything that is in a slot is decryptable, and everything that is not in this slot is not decryptable. So we kind of hard-code this information inside our proof verification, and as long as the consensus is telling us that something is in this slot, yeah, everything can be decrypted. Because the way the smart contract is designed on another level of the application.
So you have like selectable decryption.
Yeah. And also this is really like there's like a very old paper from Gentry that is explaining like how to build I/O for any program with a smaller program, what I was trying to explain before, and this is really the point. So they just kind of try to outsource the computation to some FHE system that is doing like any arithmetic operation, etc. And then the I/O is only built for the conditional decryption, such that you don't need to obfuscate like. So if you think about a program, let's say at least you reduce its complexity to FHE, which is still like order of magnitude more efficient than I/O.
So no one holds the decryption key.
Yeah.
Only the obfuscated program.
Yeah. But I think that's what I was gonna land to, because like, so if you remember, like the way we describe the obfuscation part, so there was like this obfuscate API. So I mean, maybe I will put it as a question to you, like what's still the remaining problem of this? I think you kind of were alluding to that, or I don't know if implicitly or not. So it's on the key. The issue is on the key.
The master secret key?
No, this key K. Well, also if you want the master secret key, because at the end of the day, this is the.
If someone has the master secret key, what happens?
Yeah.
The whole thing breaks?
Yeah. So if you basically but even if not only on the master secret key, but just even the key K, which is like in our application is the, for example, like the potentially like the decryption key of the encrypted blockchain.
So someone needs to have it. Is that the problem?
Yeah. So like no. Well, so the problem is that in the way that I introduced UIO, there's like on the left hand side, there was this key owner, which is a single person really. So if we think about I/O this way, like like in the, they can disappear, of course, is non-interactive, but
There's still a root user.
yeah, at a certain point in time, they had this key in their hands. So what we also want is basically some distributed setup for I/O. And so basically this is similar to like a ZK trusted setup in which everyone is kind of additionally homomorphically adding their randomness, and as long as one of them is throwing away their randomness, this is like secure. So this is like an area that in research has almost no trace. No one even figure out a problem because there are still other problems to solve before that. But we also have an idea on how to solve, theoretical idea on how to solve this problem. But yeah, so yeah.
No, go ahead. I was touching.
No. I was also getting to the final.
Yeah. So my question was about like, so if we go back to our use case about like unfolding the results of the vote and like decrypting like a specific space in our block, like how would we trust, because it's indistinguishable, how would we trust that the algorithm, the encrypted program is the right one? Like how cannot someone spoof the fact that it is the, guys, I have the encrypted program and
Yes. So I think this is like a good point. So, and we get this question a lot. So I think there are like two levels. So one is on the FHE side. So I guess that on the FHE side, on the smart contract side, you can see how the evaluation is designed. So again, let's assume that this is just adding stuff. So it's just adding encrypted vote, and it's adding to ciphertext. So this is like we can assume that this is public, okay? And so this is something more familiar that we know. But basically, this is also the same for this obfuscated program. Really, so everything that is in white in this function, so this computation, the circuit itself is public. So the person can access when they have at their disposal like this C tilde, the obfuscated circuit, they can see that they are doing like an addition, a multiplication, an addition, a multiplication. What really cannot see is this K, which actually still is FHE encrypted. I mean, this is like another level of complexity, but still in our construction, still FE relies on FHE under dual. So it's not that we get like a computational encrypted data magically. Still, we need FHE in our system.
Is the condition that makes you trust the program, because like otherwise you wouldn't be able to decrypt with a valid key assumption.
Yes.
Yeah, so it's, as you said, it's not magical. It's not like you can obfuscate everything.
Yes.
Just the fact that.
Yeah, because it makes sense. This was also like the first observation that I got is like, okay, but do we need verifiable obfuscation such that you need to prove that you obfuscate a certain program? I mean, then it becomes no, but like we don't have this issue. And so I think the presentation is over. So I just wanted to mention that we kind of did like a chain of like reduction in terms of problems. So we reduced the problem of building I/O to the problem of extending FE to this multi-input FE. So the way I describe it here is like technically this is called multi-input functional encryption, and we also reduced the problem of building this conditional decryptor to building a conditional signature printer. I mean, I don't know if it's really a reduction, but it's at least like the point that I wanted to make is that we don't need to figure out like a crazy amount of things. There are just a few very small problems, very specific problems that we need to solve in order to get to I/O. So I hope that at least now it's less scary and you might, I don't know, have a map in your mind of what is needed for that.
And what is the security? What, is it using SIS for the hard problem to solve?
Yes, so like so I'm gonna speak about the security of our extension. So I think security of function encryption, so this paper relies on evasive LWE, which is an extension of the learning with error assumption, and this is not considered a standard security assumption. And actually, the reason I mentioned that they updated the paper was an update based on attack of this evasive LWE assumption that recently happened. So, and actually in our paper, which I also gonna show, so there's this additional we also had an additional security assumption, which is all product um, yeah, so I think this is, well, I think it's not, I'm most honestly not, I cannot say I understand this. So only Sora understand this. But so there's an additional assumption that we built on for our construction, and this is actually where we get a lot of efficiency from. So really what we are also trying to do right now is trying to break this assumption, or at least get researchers to try to break our assumption. So yeah, and so the answer is that also it's not relying on like a super standard security assumption, but it's more like a creative security.
Thank you.
Thank you.